All right, this is our last lesson for chapter 8, and this has to do with a concept that you did not learn in honors chemistry, but is really important in the world of chemistry, and that concept is called resonance. Resonance is something that scientists discovered when they looked at compounds that had one or more multiple bonds, and they found something surprising. So, for example, if you look at this NO3 structure, this is just the Lewis bond or Lewis dot diagram for this. You find that if you do the dot diagram correctly, you're going to end up with a double bond to one of the oxygens. But the question is, why would you choose one oxygen over another to have a double bond? So why would nitrogen choose to have a double bond with the top oxygen and not the bottom left or the bottom right? And so scientists did studies with these, and they found that the bond energies of all three of those bonds were identical. And if you look back at the bond energy chart at the earlier pages of these notes, you'll see that multiple bonds have different bond energies, that you're going to make a stronger attraction with multiple bonds. So what they were expecting is that one of these bonds would be stronger because of the double bond, and the other two would be longer and weaker because of the single bonds. And instead what they found was that the bonds were identical in their energy, they were identical in their length, and so they had to come up with a different model to show this. And what they're showing is that, and it's kind of like that extra set of electrons gets distributed a little bit to each of the bonds. So instead of having a single bond or a double bond, you have like a 1 1/3 bond. And that's what it's showing right here in this image here. So the first one is showing all the different choices that you could have, which means that resonance is going to happen. And the second one is showing how you can show that that has a single bond and then a part of another bond. And the important thing about resonance is that it makes a particularly stable compound. And so you're going to see this a lot, especially in organic chemistry, you see this a ton. And most of the time we talked about it in terms of benzene, which is a 6-ring carbon, let me draw it first on. Looks like this. So you have 6 carbons. Each carbon has 1 hydrogen. And then you have enough electrons to make a double bond for every other bond. So you see how this would give the top carbon 4 bonds, which makes it stable. If you draw a double bond here, it makes that carbon stable. If you draw one here, it makes the bottom carbon stable. And so this is one way that you can show benzene, is to show those double bonds. But because I could redraw the double bonds, and instead of putting them where the red ones are, I could put them in place of the blue ones. I could switch it. And so how do you know which one to do? Well, a lot of times what they'll do is just draw a circle to show that it has resonance. So a lot of times you'll see it. In fact, they don't even draw the carbons when they get start to just draw symbols. That means benzene, and it shows that it has resonance on the inside. And like I said, it makes it particularly stable. And so the times that I see this on the AP exam are questions where they'll give you different structures, and they'll ask you to comment on any unusual features. And so one unusual feature could be that it shows resonance. So if you notice that there's a double bond, but you could draw the double bond in another place, that's going to have resonance. I've also seen it in like multiple choice questions where they say, which of the following has the strongest attractions or strongest bonds, or is the most stable of the compounds, and you want to look for resonance there too. So they might give you data and say, why is this one so strong? Or they might say, why are all 3 of these bonds identical? And the answer is going to be resonance. So watch out for that one as an explanation for certain things. There is something called a free radical, where you have an odd number of electrons. So most of these, your electrons are going to pair up together and you'll have an even number, but it is possible to have 1 extra electron. And if you do, just put it on the central atom. And that's called a free radical. Formal charge is the next thing, and this is where you're going to add up the number of valence electrons on a free atom and then subtract the number of valence electrons assigned to the atom in the molecule. And actually, I think if we go through one of these, it'll make a whole lot more sense than if I just read you what it says on the notes. So formal charge is a way to explain why a particular structure or a particular shape that you drew is plausible. Plausible means it's likely to happen. Because again, we can't see these things, and so all we can do is go on theories and try to predict what is the best model. So this is a way to prove which model is the best. And so what you're going to do is add up the valence electrons on the free atom. So we're going to do this for each individual atom. And so notice that for oxygen on the periodic table, it has 6 valence electrons. Then we're going to subtract the number of electrons that we assigned to it in the picture. So if it's a dot, that counts as a full dot. So notice that it has 6 dots on it. And then for the bond, we're going to cut that in half and give one of those electrons to the oxygen and the other electron to sulfur. So in the picture, we have 6 lone pair dots plus one more from the bond, which is 7. And so the formal charge value for this oxygen is going to be -1. And it'll be the same for each of the oxygens because they're all identical. Now let's do it for sulfur. If you look on the periodic table, sulfur has 6 valence electrons. And then we're going to subtract the valence electrons that we assigned to it in the picture. And again, a bond you're going to count as only 1 because we're assuming that for each bond, one of those electrons we're going to give to oxygen and the other we're going to give to sulfur. So we have 1 electron per bond, which is 4, and so the formal charge for sulfur there is 2. Then what we're going to do is add up all of those charges. So we have 2 for sulfur, and then we can combine all of the -1s, so it should be -4, and so the final formal charge is -2. Also, just as a side note, in one of my other videos, I drew the Lewis structures for polyatomic ions, and I forgot to put the brackets with the charge on the outside, so be careful, don't be like me. Make sure you put notice that I have blue brackets with the blue charge on it. You'll need to do that for all of your polyatomic ions when you do the Lewis structures. But the point is that this formal charge matches the overall charge, which means this is a plausible structure. So whatever the overall charge is for the compound, your total formal charge should equal that if it's a good structure. And then we're going to talk about, we already talked about best pair theory. Make sure you can know what that stands for and be able to explain it. This is just a picture to help you visualize all the different shapes. It kind of puts them together. So if you need a quick reference for the different shapes that we've been talking about, you can look here. And if you look down here, we talked about in one of the other videos that electron clouds take up more space than an atom, so they push harder. So if you have 4 atoms, then the bond angle is going to be 109.5. But if you replace one of those atoms with an electron cloud, the electrons are going to push on the hydrogens a little bit more, so it squeezes them down, and so the bond angle is a little bit closer for each hydrogen. And then if you replace 2 atoms with electron clouds, it's going to squeeze them even tighter. So make sure you understand that those bond angles, what they are, because in first year chemistry, we just said it was less than 109.5, but in this class, you have to know the exact bond angles. So that's what we said in first year chemistry, but now you can know the exact ones. There's a few more things. Multiple bonds, we talked about this before too. Multiple bonds count as 1 effective electron pair. So for example, if we had something like this, some people like to call this tetrahedral because they say, oh, well, there's 4 bonds, 4 is tetra, but there's only 3 outside atoms. So this is actually trigonal planar because that multiple bond right here doesn't count as, it doesn't affect the shape is what they're trying to say. You can have molecules with more than 1 central atom, and you'll see some of those. And in most cases, best pair works, which is why we buy into it. So again, it's a theory. We don't know for exactly sure, what these shapes are, but all of the data supports this theory, and so that's why we go with it. And that's it for chapter 8.